This is our second part of lesson 3. We are going to be looking at matrix multiplication. If you are immediately overwhelmed by the amount of text on the screen, pause the video, take a deep breath, and then unpause the video to come back. On this slide and the next, I am going to provide both a technical requirement and then that requirement expressed in plain English. Many of the sciences, math included, develop a very specific set of vocabulary. In mathematics, that vocabulary is also intended to communicate very precisely what a mathematician means. When we have precise language, we can communicate with each other across long distances and long times and understand what we mean. So, for example, Archimedes, thousands of years ago, used the same tools that Isaac Newton used hundreds of years ago. And because there was consistency in some of their language, we as mathematicians learning mathematics hundreds of years after their death can still look at the development of those ideas from one time to another, from one part of the world to another. And so there's importance in having consistent and precise language, but that language can sometimes be an obstacle to new learners who haven't yet developed the ear and the precision of that language, which is why it's important that I give you the technical definition, but also the plain English, this is how we make sense of it definition. We start with the simpler version, and then we can build up to the more precise definition as we understand and relate new concepts to things we've already learned. So the technical requirement for matrix multiplication is if A is an m by n matrix, so a matrix with m rows and n columns, and B is an n by p matrix, so n rows and p columns. And I do want to be precise here that when we say an m by n matrix and an n by p matrix, this n is the same number. It's possible that m equals n or m equals p or that n equals p. That part doesn't matter for the definition as long as the number of columns in the first matrix and the number of columns in the second matrix, or the number of rows, excuse me, in the second matrix are the same. So if we meet those criteria, then the product A times B equals C is an M by P matrix. Notice that the number of rows from A and the number of columns from B give us the number of rows and the number of columns in our product matrix, respectively. So if our middle numbers match, then the outside numbers give us the dimension or the order of our product. And we're just calling that product C. So we're naming our new matrix. In plain English, to see if two matrices can be multiplied, write their sizes next to each other. If the middles match, they can be multiplied, and the product is the size of the outside numbers. So if there's no match, there's no product, and as we saw before, it's undefined. So if we look at this first example, we have a 3 by 2 matrix and a 2 by 3 matrix. Regardless of the numbers inside, we can see that the middle numbers match. So that works. And our product is going to be a 3 by 3 matrix. And just in case yellow isn't displaying all that nicely on your screen, let me change the color. For the second one, notice that we have a 3x2 and a 3x2. This time, the letters do not match, or the sizes do not match. So we cannot multiply, and it is undefined. So this requirement that the interior numbers match is very important. In fact, we can dive a little bit deeper into this. Notice that whether or not we can add or subtract a matrix is independent of whether or not we can multiply those two matrices. For example, in this first one, because their orders are different, we cannot add them. And in the right example, because their orders are the same, we can add. So whether or not we can or can't multiply doesn't mean we can add them or vice versa. And so as a bit of an extension, let me type this out, that'll be slightly faster. Can you think of two matrices that cannot be added or multiplied together? And then can you think of two matrices that can both be added and multiplied together? Both of those scenarios can and do happen. And with a little bit of critical thinking and just writing down some examples of matrices that you can add like these and matrices that you can multiply like these, I'm confident you can figure that out without me divulging the response or conditions that allow these two things to happen. So I think it's a fun exercise that will deepen your thinking. To move on, once we have determined that two matrices can be multiplied, we must ask ourselves, how do we multiply them? And so the technical language says that the Cij entry, so the entry of C in row I and column J, is calculated by multiplying row I of A with column J of B and adding the products. What you will often see written out in textbooks is that Cij is equal to the sum of k equals 1 to n of ai and bj. So I also is this the proper definition? I think I'm okay. I remember the problem. So I'm missing I and j, but that's because matrices, each entry has two values. And I was forgetting that they have two values. So from matrix A, we have row I. So I is fixed and K varies from 1 to n. And for matrix B, the column is fixed, but the row varies. So we have C of C ij is given by the sum from k equals 1 to n of A ik times B kj. This is incredibly difficult to remember, and it's incredibly hard to make sense of if we haven't yet discussed what sums mean. And at least in the order that this course is written, we won't see this for a little bit. So if you were to look up additional resources, or you are coming from a linear algebra class, this would be the definition that you see. This is merely saying it in words, but for novice learners, there is a visual process that communicates this same idea more concretely. And so the process is we take the first factor and it stays where it is. The second factor slides up. So if we have A times B, we're going to keep A where it is and just push B upwards. We are creating space right here to construct our product. So to calculate the entry in row I and column J, we multiply the corresponding numbers from the I row of A and the J column of B and add their products, where I and J represent the rows and the columns numbers. Again, sometimes words are more cumbersome than pictures. So if we want to find the number in the top left of our matrix, and we have the square matrix 1, 2, 3, 4 times 1, 2, 3, 4. When we line up our matrices with A to the left, B on top, if we want the first entry of the first row and the first column, we would multiply our two numbers, 1 and 1, furthest on the outside, with our two numbers, 2 and 3, closer to the inside. So we're really going from the outside to the inside. We multiply in the corresponding positions, and then we add them together. So we would have 1 times 1 plus 2 times 3. So 1 times 1 is 1, 2 times 3 is 6. So the number that goes into our top left entry is 7. If we wanted to find the first row, second column, you'd do the first row times the second column. So 1 times 2 so 1 times 2 plus 2 times 4. So that would be 2 plus 8, 10. And then when we come down to the second row, we're changing our numbers to we're changing our numbers. So we can actually, can I stretch this out? Ever so slightly, I can. So we just changed the numbers that we're using. So here, we would have 3 times 1 plus 4 times 3. So that's 3 plus 12. So our number is 15. If we move our, oh, that's not the object. I want this one. Yep, there we go. I'll have to make our purple one a little bit bigger as well. That should be sufficient. more or less, it gets the idea across. So now we would have 3 times 2 plus 4 times 4. So we're always working from the outside to the inside on both matrices. And so this is 6 plus 16, which I believe is 22. And so this would help us determine that final matrix. So the process when we set it up visually is incredibly straightforward, even if the technical definition can be incredibly intimidating when we're novice learners. That doesn't make it impossible, but it does make it a little bit harder. And quite frankly, I wish someone had shown me this method when I was learning about matrices, because I would have understood them so much faster seeing this process. And you might be wondering, why? Why do we multiply matrices like this? And the simplest and yet most frustrating answer I can give you is because that's the way we said it should work. A lot of math are tools, and we, the mathematics community, over many hundreds of years, have defined tools that do the jobs we want them to do. And so when we need to multiply two matrices, these are the rules that make the outcome make sense. So if we are modeling the movement of an animated character in a video game, which is done using matrices, we find that the logic underlying the multiplication produces the desired result. So in a sense, we have defined matrix multiplication to work the way we want it to work. Matrices represent a tool, and some tools have a very natural function. If you think of a hammer, it only smashes things. You can use that smashing to hammer a nail into a wall, to hang a picture, or you can use that smashing to break apart a tile to use in a mosaic. There's multiple things that it can do. It's very clear from the construction of the tool that the result is you smash things. If we think of a different tool, like a pasta maker, it rolls dough through a flattening press and then cuts it into the shape of the pasta. That tool was designed intentionally to give a desired result. And the result is delicious homemade pasta, which, I've never done, but life goals. Matrices are the same way. They might look complicated from the outside, and we might wonder, why does it work the way that it does? And the reasoning, whether that is satisfying or not, is because when we use the tool like this, it works the way that we think it should. It can take a lot of extra explanation to show why we think the way it should work is the way it works. But that, to some extent, is extra fluff that even mathematicians going through years of study in linear algebra don't get caught up in. This is the tool. This is how the tool functions. This is how the tool gives us a logical result. Sometimes there literally is no deeper why than the fact that it works. And so I don't want to get hung up in that, in that frame of mind. So I want to do one more example, and then probably I'll break it into another video after that. So we want to multiply some matrices. We have the matrix 1, 4, 2, 5, 3, 6. This is a 3 by 2 matrix. And the matrix 1, 3, 5, 2, 4, 6. This is a 2 by 3 matrix. Since our middle numbers are the same, it is defined, and our product is going to be a 3 by 3 matrix. When we slide up our second matrix, notice that we have 1, 2, 1, 2. So the number of columns in the first matrix matches the number of columns in the second matrix. And we're going to multiply the parts in the first spot, and then the parts in the second spot, and then add them. And so to help make this more clear, and this was originally designed to be projected on a projector in, the before times when school was primarily in person. So I don't actually need it to be that big now. But I do think I want a new color. This one, well, it's quite pleasing to the eye. I'm getting bored with it. So we always start from the outside going to the inside. If I want the if I draw a line through the first row and then the line through the first column, where these lines meet is where the product goes. Let me change back to the pen. So we have 1 times 1 plus 4 times 2. So that's 1 and 8. So we have 9. Then I'm going to, we could go in any order. We could do the next row down. We could do the next column across. Because we read matrices from left to right, row by row, I like to multiply in the same order. So I'm going to slide my point of reference over to the right. I know this is easier to do on a computer than on paper, but on paper, if you can imagine holding your hand or your fingers over the other columns that you're not interested in, that can help visually align ourselves. So then we would have 1 times 3, always the outside numbers first, plus 4 times 4. So that is 3 plus 16. So this would, that should be a 9. So this is 19. Once more, slide our point of reference over. And then we have 1 times 5 plus 4 times 6. So that would be 5 plus 4 times 6 is 24. And this would be 29. Now we can slide down to the second row. I'm going to reset my column back to the first column. And as we go through this, we will continue to see the same pattern. So notice that our first numbers are now 2 and 5. So we'll have 2 times 1 plus 5 times 2. And this would give us 2 plus 10. And 12 goes into our matrix. I want to point out a couple more patterns to help make them more apparent. I'm going to slide down to the third row for a moment. I know that goes against the idea of filling in row by row, but I want to illustrate an important point. So now we have 3 times 1 plus 6 times 2. So that's 3 plus 12. So in our bottom left corner, we have 15. And so the point that I want to highlight is some of this pattern inherent in what we're doing. So if we look at this first column, that actually is a really bad color right there. If we look at this first column, I'm not liking how that appears. If we look at our first column of computations, notice that the second number for each multiplication is the same, and the only things that have changed are the numbers that come from the rows, which is what we changed going from the top to the middle to the bottom. If instead we look at the first numbers, all of the multiplications, if we go left to right, have the same numbers in the first position. So those are the numbers from our row. So there's this internal consistency in how the numbers change from place to place in the full matrix. And so this can help us as we're doing our scratch work to double check that we are changing the numbers in the right place for the right space. So I would like to encourage you, if you haven't already done so, to pause the video, finish calculating these next 4 places, and then in a moment, I'll just finish writing them. Of course, it would be helpful if my computer doesn't freeze a bit, but you know, technology can't live with it, can't live without it. There we go. I'm going to do this in a different color because I'm going to rush through it so that you can check your work. So yeah, the work will be a little bit more sparse on the page. So for this next one, we have 2 times 3 is 6. And then 5 times 4 is 20. So 24. Then we have 2 times 5 is 10. Plus 5 times 6 is 30. Then we have 3 times 3, so 9. Plus 6 times 4, 24. 33. And then 3 times 5 plus 6 times 6. That would be, let's see, 36 plus 5 is going to be 41 plus another 10, 51. So that concludes our multiplication. As I said, I will do additional examples, but I'm going to do them in a follow-up video to try to keep these as short as possible.